Mark, I think we can start. I see the numbers have slowed down in terms of people entering. So I'd like to welcome everybody to this webinar session hosted between ElectroMechanica and Hager. I'm in South Africa, and Mark, you are in France.
France.
Yes. Bonjour.
Bonjour.
So before we start, a bit of house rules. So the presentation will take around 30 minutes. It will be presented by Mark, who's at Hager. Questions and answers will be after the session. It'll be about 15 minutes. If you have any Q&As, there is a Q&A tab at the bottom. You'll see it's next to participants where you can input your questions. Maybe just if you have a question on a specific slide, you can put the slide number or the topic that's being addressed. In terms of interaction, just be a bit respectful, foul language on the chatter or comments, and we will also be sharing this webinar or the presentation afterwards. Thank you for joining us, and everybody enjoy the session. Thanks. Over to you, Mark.
Thanks, and thanks to giving me the opportunity to present a topic. I will share my screen, and then we can check. Okay, good. So then let me start. The topic of today is earth leakage protection challenges in PV installation, and I will present the current situation. What is the issue? What is the problem? Remind you what an RCCB is for, and then help you finding the root causes and offering support and solutions to solve these problems we have in the field. So the current situation in South Africa, we have now 5 to 10% of residential market installed, and most of times the PV panels are associated to a storage. And you see, I guess you know better than me all these informations. Batteries from 5 kilowatt hours to 20 kilowatt hours average. And yes, there are some inverter brands, and these are not off-grid. We have sometimes off-grid, but here the issue is with the on-grid systems, and especially when the grid comes back. So that means from time to time you are completely off-grid. And what we understood, so this is typical installation. We have the PV installation, we have this inverter, we have the RCCB, we have the building and the grid. And the problem occurs when the grid disappears. You are powering the house with off-grid. You are disconnected from the grid. And when the grid comes back, there is some tripping of the RCCB. So what we think is that when an RCCB trips, it's because of an earth leakage. And each inverter has a common mode filter. And what we think is that when the grid comes back, there are some transition currents that are filtered by this common filter, and generate some leakage, and this leakage is seen by the RCCB, and therefore it trips. So that is what is written here. We suppose that it's probably due to this common mode filter, but we'll see this later on. We have to investigate a little bit deeper to be sure that that's the right analysis of the situation. These RCCBs are intended to protect people, so they trip when the leakage is above 30 milliamps, and this stripping occurs within 300 milliseconds. This is what is required by the standards. In fact, for high immunity and B-type, having electronic assistance, it's about 220 milliseconds. For a classical tape I, With no electronic assistance, the tripping occurs within 40 milliseconds. So this is more maybe a reminder for you. Why do we put RCCBs in electrical installation? It's to protect people. It's not to protect the goods or the building. It's to protect people against danger of electricity. So when somebody gets in touch with an electrical conductor, there is a current going through his body, going through the earth, and the RCCB is detecting this current going through the body of somebody. And if it's higher than 30 milliamps, the RCCB is tripping to protect the person of the dangers of electricity. These dangers are described here. You see on this graph, on the vertical axis, you see the duration of the current. And on the horizontal axis, you see the current crossing the body of the person. So the limit was defined at 30 milliamps, and the tripping time, according to the standards, has to be under 300 milliseconds. In this situation, there is no risk for the person. You see on the right side the different colors. So green stands for no reaction. Yellow is you can feel it, of course, but there is no dangerous consequence for you. Orange becomes to become tricky, and red is really dangerous because you are unable to release the conductor. You stay blocked on the conductor, and if the current goes on, you will have problems with your heart, and this can lead to death, of course. So that's for the RCCB and why we put an RCCB. Here we put an RCCB because the inverter is considered as a source of power, of course, inside of your building. And therefore we have to protect the line that is downstream of this source of power. And in our situation, the RCCB is doing its job. It means it has to trip when the earth leakage is above 30 milliamps. That's absolutely normal. Increasing this threshold of the RCCB, you know, there are RCCBs with 100 milliamps or 500 milliamps, even more. This could avoid the tripping in case of high transition current. But of course, the people would not be protected anymore. So this is not a solution to change the RCD to put a higher threshold. Cannot be a solution in this case. So here we go through the different types of RCCBs existing in the market. So you have the classical old AC type, which is no more used. What we sell, for example, is only A type. So the A type is able to do what the AC is doing, but he is also able to detect pulse current leakage. For these devices, the tripping time is about 40 milliseconds because there is no electronic assistance. We propose also high immunity. At Hager, they are called Hager immunity. These devices do the same than AC and A, plus immunity and surge current. That means there is electronic assistance, and this generates a delay. That's what we call immunity. There is a delay because we have to charge some capacitors, and this takes time. And therefore, the tripping is always according to the standard, which is 300 milliseconds. But the tripping time goes from about 40 milliseconds to more than 300. Most of the time, we have 220, 230 milliseconds. So for some critical situation, this can help to prevent trippings that are not wished. We have also in the pipe the F protection. This will be the next high immunity product, which will be able to do the same than the high immunity, but is also able to work on different frequencies. This protection type is specially intended for converters and power electronics. So you will be able also to detect currents occurring at a frequency of 10 hertz, 50 hertz, which is standard grid frequency, and 1000 hertz. And this product will combine these three frequencies to provide a better level of security. These products are not available today. They are in development, and I guess they will be available in the market within, let's say, 2-3 years. We have also the B type. The B type is F-type with direct current. This product is able to detect direct current leakage and to trip. And we have the B plus protection, which is a B type, which is not available today, but that's future, with high frequency protection up to 20 kilohertz, intended for fire protection, the kind of arc fault detection, more or less. So that's what is existing today in the landscape as RCCBs. What is important to know is when we speak of tripping times, so I mentioned 40 milliseconds and I mentioned 200 milliseconds. This is for the nominal differential current. And here we are speaking of 30 milliamps. This is our nominal differential current. Here you see on this diagram, you have the tripping time in milliseconds on the vertical axis, and on the horizontal axis, you have a ratio going from 1 to 10. 1 is 1 time the nominal differential current, so it's 30 milliamps. 2 is 60 milliamps. 3 is 90 milliamps, etc. You see that above 5, so 5 times 30 is 150 milliamps. Even the high immunity RCCB is tripping very fast, same speed as the classical one. So we are then also at 40 milliseconds. The type A is not sensitive to the level of differential current, or very, very few. But the classical high immunity is sensitive to this. Therefore, it's important to know what is a real leakage current, what is the value, to know what could be the appropriate solution. Because if this current is very high, even high immunity products won't work, because they will trip too, because the leakage is so high that they will trip quickly. That means quickly means before this transition is finished. So now what should we do to solve this problem? The first thing to do, and we are as Hager, we want to propose support to help you, but we need some more information about the situation in the field to understand what is really going on. So the first thing to check, is there a permanent leakage? Because if there is a permanent leakage, of course, the remaining gap for transition will be reduced. Now you can see it on this chart. The threshold is 30 milliamps. If I have permanent leakage, I have only 15 remaining for the transitions. That's one point. And the second point, of course, is to understand what is going on during this transition. What we guess is that there is a kind of peak during this transition. And if this peak is below 30 milliamps, nothing happens, of course. If it's above, the RCCB will trip. So how to perform these measurements? You have to use a measurement core and to put it around all the conductors because what we want to measure is leakage. That's the difference between it's a sum of all the wires, the three phases and the neutral. You have to measure them together, and this will give you the residential current, in fact. And the best is to use a oscilloscope to make this measurement, to see the evolution over the time, and also to have not only the current, which is the most important one, but also the voltage and frequency. What you can do is to use this oscilloscope to make this measurement. You can measure the permanent leakage in on-grid situation. You can shut down the grid and see what happens during this first transition. But apparently, when the grid shuts down, there is no problem of tripping, as far as we understood. The problem occurs when the grid comes back. So you can switch on the grid and to measure this transition leakage current and see if the RCCB is tripping. And this would be helpful to know about the level of the currents, also the duration of the transition. We are happy to get this data from you and to analyze them and to give you some advices to confirm the root causes and to make some recommendations. So based on these measurements, as I explained, we can analyze the default, confirm the roots, root cause, what I said. What solutions can we imagine? We could imagine to put a second common filter between RCCB and distribution board. So I come back to my diagram. Here we have this common filter associated to the inverter. And if there are transitional currents, they will go through the RCCB and will be evacuated to the earth by this filter. So the idea would be to put a second filter between the distribution board on the very right side and the RCCB, so that the RCCB doesn't see these transitional currents coming from the grid. And therefore, we think we could avoid the tripping, because instead of evacuating this current after the RCCB via the common filter of the inverter, we will do it before. Another possibility, and this is depending on what I explained about the curves and the levels of leakage current, would be to use the type F that will arrive in the market in the future, but you can still use high immunity products. High immunity means with electronic assistance. RCCB is having electronic assistance because these products are tripping with a delay. So instead of tripping with 40 milliseconds, they trip with more than 200 milliseconds. And this could be enough, again, depending on this transition current. This could be enough in some cases to solve the problem. And that's it for me. I was a little bit quicker, but this is what we can propose for this topic, and this is our understanding of the topic. So now we can, if there are some questions, I would be happy to answer. I would also like to get your feedback about our understanding of the problem, and if you think that what we can offer makes sense for you, or if you knew already everything I explained today.
Thank you, Mark. Yeah, is there any questions? Yes.
There is one hand raised, I see.
I see. You can add your questions in the Q&A. I see Shulk. Do you have any examples on the filter?
There is Biomba Kapajika wants to speak.
Oh, okay.
Maybe.
Yes,
Yes.
I have a question.
Yes, please.
The capacitor that you're talking, I've got two questions. First, you say about the positioning of the capacitor. It must it be between the main DB board of the house and the inverter, or must it be before the supply coming from the grid to the main DB of the house? That's the first question. The second question is, how do you know which size of filter must you use? That's my second question.
The first answer is, if you want to filter, you have to filter between the distribution board and the RCCB protecting the inverter. So you are not obliged to do it close to the grid. You can do it. You have to do it on the line between the inverter and the distribution board. And depending concerning the size, we have to know what is the current leakage level. So if you are able to measure, we can make you a recommendation about how to filter this. So I just show you the position again. If you have this diagram, you have to put the filter here so that he will send the leakage to the earth here so that the RCCB won't see anything. The RCCB continues to see the current coming from the inverter, which is stable.
Okay. Skulk, sorry. Put in the Q&A. Do we have an example of the filter?
We have some examples. I have to exchange with my colleagues from the sales team what we can do. I think we can propose some solutions, but we have to double check, and we have to check if we have solutions at Hager or if we can recommend solutions in the market. I will make this via ElectroMechanica and our Hager sales team.
No problem. Thanks, Mark. And yes, to everybody that's asking, we will be sharing these presentations afterwards.
Yeah, of course, no problem to share it.
Is there any other questions? You can raise your hands or put in the question. Yes, Ampo, I will be sharing the recording as well. Reagan is asking, will there be generic sizes depending on the size of the inverters? It might be difficult to design per leakage size.
I guess we can find one solution that works in most of situations. So we don't need to have a big range of filters. Normally, one filter should do the job for all situations. Of course, if it's big, very big industrial installations, it's different. But here we are speaking of residential, maybe small commercial buildings, and then I guess it should be quite easy to do it.
Okay. This answers your question, Reagan. Perfect. Do you perhaps, Mark, have a picture or a photo of the filter?
Of the?
Of
No,
the filter.
I don't have it here. I have one. I can show it because it's an old product we had.
Mm-hmm.
Let me just check 1 second. It looks like a modular device, and you don't need to put it in series, you can put it in parallel. I give it just as an example. It could be something like this. You see here? You see my screen still?
Yes.
So it looks like this kind of product. You see, it's modular devices, and again you can put them in parallel. Yeah, and you see you have different capacities. So depending on the level and on the configuration, we can make recommendations. But these products are not existing. So I show you pictures of things that are no more existing. But we can find an equivalent solution and make recommendations for you because this type of products are existing. It's not rocket science. It's just a capacity. If it's a combination of resistance and capacity to filter this leakage, these perturbations coming from the grid when the grid recovers, and to send them in the grid in the earth. Sorry.
Okay.
It's not a huge thing. It's not a huge beast. It's a modular product, again connected in parallel on the installation. So you don't need to interrupt the connection. You can just put it as an add-on, and you connect it on the connection coming from the distribution board or from the RCCB. It has to be upstreams of the RCCB when you come from the grid side. That's a rule.
Okay. We have another question here. Sometimes I have noticed that if the inverter and the battery are not earthed properly, this also causes tripping. Do we have any cable size recommendations?
Cable size?
Yeah.
Between inverter and battery?
Correct. They're not earthed properly.
There are rules related to the. You mean size, the cross section or the length?
Biombe? Earth cable. He's asking about the earth cable.
Sorry?
He says the earth cable. Do we have any cable size recommendations?
As an earth cable.
Yeah. See,
I cannot answer this, but I take the point.
Mm-hmm.
But earth cable is more about resistance. What is required most of the time is a resistance value of the earth cable. It's not a question of section, because when you put this in the is it the earth going really to the earth, you mean, or the earth going to the distribution board?
What I'm trying to say is I've had it like 3 or 4 times where the client complained about the tripping of the air leakage. And 2 times I noticed that the inverter was not earthed. The casing of the inverter was not earthed, neither was the battery. So sometimes I use the 2.5 mil cable. It solves the problem. Sometimes it doesn't work. So I was wondering, maybe the earth cable need to be bigger? Maybe use a 4 mil or 6 mil cable to do that, because the tripping of the air leakage is sensing any current leaving the circuit. So I don't know if I'm making sense.
I can take the question. I will discuss with our battery inverter experts we have in the group. I will ask them the question if earthing of inverter and battery, if there are some rules about the cable cross section. I will send the answer to ElectroMechanica. They will forward you the answer then. Huh?
I see Hercules did respond here. His recommendation is a minimum of 6 millimeter for the earth cable.
Mm-hmm. And normally there is no current in the earth cable, so I'm a little bit surprised, but I will double check.
Danny asks, does the output of the inverter to the RCCB only comply to socket outlets? Can you leave things like lights without earth leakage?
I'm not sure I got the question.
Does
when
the
you have output of the inverter,
to the RCCB only comply to socket outlets, i.e. the plugs? Can you leave things like lights without earth leakage?
Light, when there is no earth leakage, I don't see a problem. Huh? The problem is when there is earth leakage. Stripping is only due to earth leakage. So a classical lamp, if it's LED, for example, there is no earth leakage with LEDs. It was not the same with these neon bulbs. In the past, they used to have a lot of earth leakage, but now with LEDs, we don't have this problem. So I don't think this is a problem. I guess, and again, we have to confirm this with some measurements. There is a transition when the grid comes back. There is some transition current that generates this leakage, and this filter embedded in the inverter is doing his job. And when he does his job, the RCCB trips. That's the reason.
Okay. There's another customer saying, sometimes we have sites where the earthing is correct and there's no visible installation faults. However, the motorized breakers are not engaging after load shedding.
So can you please repeat? Sorry.
Sometimes this customer has sites where the earthing is correct and there's no visible installation faults. However, the motorized breakers are not engaging after load shedding.
And what is the question?
He just wants some assistance with that. He doesn't. Is there anything that he might be missing? Maybe Impo, what we'll do is we'll go offline. This sounds more of an application issue, and we'll get in touch with you to see how we can assist with the application.
Yeah, maybe we have to go more in details.
Yeah.
Because
we'll note
we
this
have to understand
touch.
better the problem.
Yeah.
At least for me, it's not very clear. And we can propose if for some dedicated problems, we can also have organize a team meeting with our experts from the lab, and to give some explanations and advices if you want. Yeah, we are fully open for this.
No problem. Reagan did mention that these questions are related to SANS 0142 specification. Maybe other colleagues need to review the SANS spec on the earthing sizes. Thanks, Reagan, for that.
Yes.
Somebody did mention anonymously, normally specing the earth cable to the same as your current supply cable, although there is no NBO current in the earth leakage. When there is a leak, it needs to carry the load, which you'll be able to produce. That's just a comment somebody made. Thank you for that. Is there any other questions with regards to earth leakages in PV installations? If you do have any questions, you can contact ElectroMechanica directly, and we'd be happy to assist you.
And we would be happy to get some measurements in the field to see the shape of the current and to see what is really going on, because this would help really to understand and to propose the right solution. Yeah? If not, the risk is to have some general statements and maybe solutions that are not efficient because we didn't really understand what the problem is.
Definitely. So I know for attending the webinar, we have a competition for some Bluetooth headphones. We'll do a random draw afterwards of all the attendees, and we'll be in touch with you directly to send this through to you. So thank you everybody for attending. Thank you, Mark, for this
Thank you.
informative session. And yeah, we'll keep in touch.